Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we will start looking at the WDM components that make up an optical fiber communication system. And we specifically call this as WDM components because WDM is the standard technology that is used in optical communication systems. The fiber bandwidth is divided into multiple bandwidths, okay, each in the frequency domain or frequency division multiplexing way. But because of the use of wavelength or the natural unit of light measurement, measurement. So, we normally talk about wavelength division multiplexing, although the concept is essentially the same because wavelength and frequency are related in a one-on-one manner. So, you could of course talk about frequency division multiplexing, but because of the wide use of wavelength instead of frequency as the unit, we call this as WDM or wavelength division multiplexing. And this is wavelength division multiplexing, as I said, is because you take this total available band and then you divide that band into multiple short bandwidth sections, okay, and each bandwidth or each channel, as we would now have, will have a central carrier and an allocated bandwidth to it. This bandwidth can be represented in terms of the wavelength, as I have told you, or equivalently in terms of the frequency. We will switch between frequency and wavelength depending on the context. Hopefully that should not be too confusing to you. So, you have these multiple channels. So, this is channel 1, this is channel 2, channel 3, channel 4. A good optical fiber communication system which is well standardized can support up to 200 WDM channels with a spacing that goes anywhere from 50 to 100 gigahertz. So, there is this dense WDM systems with 50 gigahertz, but normal WDM systems are at about 100 gigahertz. Earlier they were about 200 gigahertz. Even earlier, before we could get to these WDM components, right, there was also something called as coarse division multiplexing. In the coarse division multiplexing, the bandwidth separation was quite large. Okay, here the bandwidth separations are about 0.8 nanometer, reduced to 0.4 nanometers in many cases, 0.4 nanometers in dense WDM case. So, what are these WDM components that we are talking about? First, if you look at the fiber itself, as I said, the fiber has the capacity of carrying many channels. So, you have your channel 1 with some data that is coming in from a user or some other computer terminal or an aggregate data or voice data that could be coming in from. So, there are various data that from various sources you can actually get this data, and then you have these multiple channels. Each channel of course is centered at different frequencies or equivalently different wavelengths. So, this wavelength, say lambda 1, this is centered at lambda 2, lambda 3 and up to the last wavelength lambda n. Each of them has a certain bandwidth allocated to it. So, this is delta lambda, and we simply assume that this delta lambda is equal for each of the channel. Of course, each channel can have its own user data or own data out there, and the objective of this WDM system is to somehow combine the data that is coming in from different channels and then to launch into the optical fiber, where at the receiver side you should again be able to demultiplex them or remove their combinations, and individually you have these different channels. Again, these channels are settled at lambda 1, lambda 2, lambda 3 and so on up to lambda n, and you need to be able to get the data out. So, I will call this out data as data with a hat on top of it to indicate that there are situations where this data may not be exactly equal to the data that you have transmitted because of the errors that have been made. Okay. So, what technology can combine this, or what is the device that can combine all these channels? It turns out that there is a device called as WDM multiplexer. See, we just tag on the word WDM for many things. Okay, it's actually a multiplexer that we are considering, and this is a multiplexer that is multiplexing signals of various bands or various channels which are well separated in the wavelength domain. So, on the wavelength, these channels are all separately occupying their own slots, that is, data is occupying their own slots in their appropriate channels. What this WDM multiplexing will do is to combine all these optical signals into one stream, and then it will launch into the optical fiber, and these are combined at the same time. So it's not like you first take this lambda 1 launch into it, lambda 2 launch in, and so on. So they are all combined at the same time. Okay, so that is the WDM multiplexer's job. And at the receiver there is something called as a WDM demultiplexer. Okay, so a WDM demultiplexer will demultiplex all the channels and thereby allowing you to obtain individual channels out there. So you have a WDM mux and then you have a WDM demux. Okay, this is not at all the end part of what is WDM. Suppose at some point I want to break off this optical fiber, okay, or to actually get some of the signals that are, instead of routing them through this way, I want to route them to another optical fiber, right. So if I want to do that one, I need to be able to first couple light which is traveling in this direction on this waveguide to be traveling on the other waveguide. So what I need is some way of branching out an optical signal, okay, and sometimes I do not want to branch out a signal, I want to actually combine the signal. These two are complementary devices, they are actually passive bidirectional devices, meaning that when you send in an optical signal in this way, the optical signal separates out into two components. It will be the same information, maybe some phase change will happen, but essentially it is the same signal that is going in this one. So this, for example, is maybe say Delhi to Kanyakumari. So this is the optical fiber that we are using there. But if I want to send the signal to say Jaipur, this would be the fiber that I have laid, which will carry signals from Delhi to Jaipur. Okay, so the optical signals that are being carried, or the WDM signals that are propagating from Delhi to Kanyakumari, if some of them have to be routed to Delhi to Jaipur, one way would be to copy the entire stream. There are better ways of doing this, I will tell you the better ways of doing this one, is to first copy the entire different channels. So these are all different channels. So this is channel 1, channel 2, channel 3, channel N, and so on. So same thing, you copy everything here, okay, and then you select only one of them. So maybe only the channel 3 is supposed to go to Jaipur. So you select only one of them and then reject or suppress all the other wavelengths. So you do not have any wavelength here, no wavelength, and then this wavelength has been selected and again no wavelengths, and you pass it on to whatever the processing unit, local processing unit that is there in Jaipur route. Okay. So this requires, of course, to actually have the ability to have these devices which will be able to copy the signal onto the other branch. Maybe when they copy, there will be some amount of delay in, or some amount of phase shift that is possible, but it is still possible for us to actually make devices which will allow you to copy the information in more or less the same fashion. And these devices are called as Y branch devices. One which actually splits the signal into two is called as a splitter, and the other one which combines is called as a combiner. Together sometimes they are called as couplers. Okay. These couplers, as I have told you, a lossless coupler will actually take the input signal and split it into two equal parts or maybe different parts, but the total energy in each of them arms when you combine them will be the same, or if you individually calculate will be the same. A combiner will take inputs from two different optical fibers and then give you the single optical fiber which will carry the signal. So this couplers is also a very important device for us. Okay. Now instead of a coupler, we might elect to use what is called as a circulator. Okay. A circulator is a very interesting device. What it does is, it actually has 3 ports. We will talk more about all these devices. I am just giving you an overall idea of what are the different WDM components that we use. Okay, so this is port 1, port 2, port 3, and the working of this circulator is actually dependent on the direction of the arrow. So the direction of the arrow seems to be like going from 1 to 2, which is correct, and then what it does, what it says is that this arrow continues in this manner. So it goes from 2 to 3. So this circulator, okay, is a very important device in what is called as optical add-drop multiplexers. Okay. What is an optical add-drop multiplexer? Suppose I have signals coming in from 3 different channels. So call them as channel 1, channel 2 and channel 3. What this circulator does is to take these signals from port 1 to port 2, not to port 3. So port 1 to port 2 is called as the transmit port. Okay, there might be some loss which we will call as port 1 to port 2 transmit loss, or simply port to port transmission loss. Okay, so port to port transmission loss is possible. Okay, and this is the transmit port. Of course, now what happens, all these signals are copied onto second port, the same signal. So these are the channels that we have copied. So let's make them lambda 1, lambda 2, lambda 3 to remove any confusion between the port numbers and the channel numbers. Suppose here I put in a selection of filter, or actually maybe we should have taken this one in a slightly different manner. So let me just go back to it. Circulator is fine. So the way to put that one would be slightly different. So I will actually have a circulator itself. So I will have a circulator here, 1, 2 and 3 ports. Okay. Now here I will have a filter, but I don't have any filter. I have a very specific filter which I will call as a fiber Bragg grating. Okay. So this is a grating actually which is created out of an optical fiber itself, and this specific grating is called as a fiber Bragg grating, and this will act as a filter or a selective component. And the characteristic of this fiber Bragg grating is that it can be tuned to a particular wavelength. For example, I will tune this to say wavelength lambda 3, so that it will allow. So you had this lambda 1, lambda 2, lambda 3 incident on the fiber Bragg grating, but what this fiber Bragg grating will do after it has been tuned to lambda 3 is that it will allow lambda 3 to pass through, lambda 1 and lambda 2 are not passed through, or lambda 1 and lambda 2 are rejected by the fiber Bragg grating. So it will actually carry only lambda 3 out. Okay, and it will actually push or reflect back lambda 1 and lambda 2. So you have these two channels which are now reflected back, and then they start moving towards the circulator. Okay, so as they move to the circulator 2, will they go to port 1? No, they will go in the direction that is indicated by this arrow, which means that they will be copied back onto this line. So out on this line you will have lambda 1 and lambda 2, and this is how the circulator will actually behave. So a circulator will take an output, will take the direction in which the arrow is pointing. So any signal that is launched along 1 will go to signal along 2, no signal will go from 1 to 3. Of course, in reality you cannot have that no signal will go through. There will be some amount of leakage signal onto lambda 1, and this is called as isolation of the circulator. So we call this as port 1 to port 3 isolation. Isolation simply means that how much of the power in 1, that is port 1, is being rejected by port 3 or the device. Of course, it will still send out some residual power here, but how much is the difference here? So if you have launched 1 milliwatt here and you get just about 1 microwatt here, then this device has about 1000th order of magnitude, or about 30 dB isolation between the two ports 1 and 3. Of course, it is the same notion that when you send in signal at lambda 2, no signal will go to lambda 1. Of course, in practice there will be some residual signal from port 2 appearing in port 1, and that would again depend on what is the port 2 to port 1 isolation. So this device that we talked about, which is a combination of a fiber Bragg grating and a circulator, is called as optical add-drop multiplexer. Okay. The reason why we call this as optical add-drop multiplexer is because I am able to, of course at this point it's just kind of rejecting kind of a thing or rerouting kind of a thing, but it can be converted into a add-drop multiplexer as well. Here we call this as, this is the transmit, okay, and this is this lambda 1 and lambda 2 are said to be dropped. So this is the one that is being transmitted, and lambda 1 and lambda 2 are being dropped by this FPG. Of course, you can keep multiple FPGs, okay, such that when you tune this to say lambda 3, you can tune this to lambda 1, lambda 3, and in between you can keep these circulators so that they can all come back appropriately spaced, and then you can combine all of those into a single this one device by using a combiner, right. So this is my combiner. So signals can come, lambda 3 and lambda 2 maybe for example are being transmitted or are being dropped, and they can be picked up by a single fiber by this combiner. Okay. This is another WDM component. Of course, this component you have already seen. This is the fiber, or this is the amplifier. This is the device, I mean this is the symbol that we use. We do not actually use the fiber symbol to denote the erbium doped fiber amplifier, but this is the fiber that we have seen, and this amplifier can itself occur in 3 different ways. So you have, this is also a WDM component by the way, and as we have also seen, this the EDFA to operate requires a pump, right, and this pump is usually a laser diode sitting at 980 nanometer. So you need to have a signal coming in from 980 nanometer on this blue line, okay, and the signal which is at 1550 nanometer should also come in on the red line, and you need to have a device which can combine both 980 nanometer signal and a 1550 nanometer signal, okay, and then pass it on to a single output, and such a device is called as pump WDM coupler, okay. Pump WDM coupler, because pump is at 980 nanometer, 1550 is actually the WDM channels. So you could simply call this as pump coupler, or we call it as pump WDM coupler, okay. So that is that one, and this is the erbium doped fiber amplifier, which of course amplifies and things that you already have seen. So we have talked about this erbium doped fiber amplifier. Of course, the same symbol is also used for semiconductor optical amplifiers. In this case, there is no pump coupler requirement because the pumping is done by the current of the semiconductor optical amplifier, okay. So this is also a WDM component because it is used in WDM systems, and this EDFA is used in 3 different ways, okay. So first way is when you have a transmitter, right at the output of the transmitter you place a erbium doped fiber amplifier. This is called as a main amplifier. Somewhere in between the fiber you can use, this is called as the inline amplifier, okay, or sometimes called as the, so this main amplifier is sometimes called as the booster amplifier, and this is the inline amplifier which will actually compensate for the losses. And at the receiver side, just before you place the photodetector, so now this is the photodetector, and just before you place a photodetector you can actually have a erbium doped fiber amplifier, and this EDFA here is called as the pre-amplifier, okay. We will see that the noise characteristic of pre-amplifier followed by photodetector is a very interesting and important information, and this will affect our performance of the system because it changes the noise characteristics totally. We will study that in detail once we kind of look at all the other WDM components. So this is something that we will revisit, the combination of an erbium doped fiber amplifier, which is a pre-amplifier, and the photodetector. Of course, at all these places, especially in when you are looking at these pre-amplifiers, or you are actually looking at amplification in general, whether inline or booster, you normally also follow up, or you, before you give signals to the optical amplifier, you will also actually put in a device called as a filter, okay. And this filter can be single band filter or it can be multiple band filter, and the ways to make these filters as WDM filters is also something that we are going to talk about it sometime later as we look at the WDM components. And the job of this filter is essentially to limit noise, okay. But as I said, you could of course take a WDM channel and then select a particular channel. So maybe this selection of the channel would be lambda 3, so that others are suppressed and there is a lambda 3 which comes in at the output, okay. Of course, the lambda 1 and lambda 2 are not being reflected back, so this is different. So this is just a filter, this is not the same as the fiber Bragg grating because it does not reflect back anything, it simply absorbs the whole thing, okay. So the characteristic of this filter is not the same as that of the fiber Bragg grating. So we have seen these devices, which all of these devices starting from WDM multiplexer, demultiplexer. In fact, WDM multiplexer and demultiplexer are essentially filters themselves. So this is how the multiplexer characteristic would typically look like. These are the central bands, and this is how the overlapping actually happens. So one has to design a filter such that this overlapping can be reduced as much as possible. And a demultiplexer also looks very similar to this one, except that there are these individual channels out there at the output, whereas at the input you have all this single channel, okay. You can separate them out by another WDM device called as an arrayed waveguide grating. This arrayed waveguide grating will actually be an array of different waveguides, okay, of different waveguides that come in out there, and the selectivity, that is which grating takes upon which. So there is a fusion out there, so you actually fuse the input and output out there using a splicer or some kind of a fusion splicer, and each of these will be at different wavelengths because they will be having a certain orientation and they will be having a certain length adjusted according to this. So we will talk about these devices also if time permits. Otherwise, you just have to remember that arrayed waveguide gratings is another way of separating out the different components. Okay. We of course have seen couplers, which will be very important. Couplers can be made to work as splitters or they can be made to work as combiners. They are passive bidirectional, meaning it does not matter which way you put them together. Okay. And we have seen these circulators, we have seen fiber Bragg gratings. There is another device, WDM device, which is kind of a grating itself, or which is actually a grating, called as long period grating. Okay. Long period grating, as its name would suggest, has quite long periods. Okay. Period means periodicity in the refractive index variation, and these are usually used to couple the modes from cladding to the core. So they actually do a core to cladding mixing up of the modes, and they are widely used as gain equalizers. Okay. What is the meaning of gain equalizer? We know that the erbium doped fiber amplifier has a gain cross section that looks something like this, from say about 1526 to 1560 nanometer. So clearly the central one near 1550 is the one that is actually getting lot of gain, but the others are not really that equal in terms of the gain. So if you have multiple channels here, it is clear that the central channel where the gain is peaking will have the higher gain, while the others will have a lower gain. But using these LPGs designed carefully, you can actually have a gain profile equalized such that this will be the inverse filter, which has almost the same shape as the gain filter out there, so that overall you will essentially have a uniform gain from 1526 to 1550 nanometer, so to speak. Additional WDM components are polarization beam combiners and polarization beam splitters. Okay. These are devices which are used to combine polarizations and to split polarizations. They will just be concerned with their polarization components. Then there is also another device called as isolator. Okay. This is also a very important device because it can what the isolator does is it will allow the light to propagate in the direction of the arrow. It does not allow the light to propagate in the reverse direction. So if the light tries to travel from here, it will block this one. Then there is what is called as a Faraday mirror. Okay, so Faraday mirror will simply reflect whatever the light that has been sent in onto the reverse side of it. So this is another WDM component that will be very useful to us. So you have an isolator, you have a Faraday mirror, you have all these devices which are used. Interestingly, these polarization beam combiners, polarization beam splitters, isolators can exhibit some polarization dependencies, but they can be made to be polarization independent, and all these devices work on the basis of what is called as Faraday effect. Faraday effect changes the state of polarization. So if you send in a linear polarization in one direction, it may turn out to be linear but with an angle 45 degrees at the output, but if you send in a 45 degrees at the other end of the fiber, that is from the other end, at the output it won't go back to the linear polarization. Okay, it will actually do one more 45 degree rotation, and then you will actually get light which is horizontally polarized. So you started off with a vertical polarization, you got a 45 degree polarization, but you take the same 45 degree polarization and pass it through the device in the backward direction, well, it will turn out to be a horizontal polarization. Okay, which means that state of the polarization rotates only in a given direction, it does not change the direction. So these are all the different WDM components. I have given you an overview of these components. We will look at the operating principles of some of these components starting with the coupler in the next module. Thank you very much.